Publish-subscribe pattern, the backbone of modern distributed systems. What do tech giants like Netflix, Uber, Amazon, and LinkedIn all have in common? Behind the scenes, they rely on one insanely powerful concept that every top backend engineer and distributed systems expert absolutely must understand: the publish-subscribe pattern. And here's the really exciting part. This is not just another theory explainer. This is the exact kind of architecture that helps engineers crack interviews at companies like Google, Meta, Microsoft, and Uber. Why? Because it teaches you how real internet-scale systems actually communicate. But instead of boring diagrams and dry explanations, we're going to learn this using anime-style storytelling, fun visual analogies, and real-world system design scenarios. You'll see how messages flow across distributed systems, like secret missions being passed between anime characters, how millions of events travel without services even knowing about each other, and why a single mistake in handling duplicate events can literally break production systems. So, here is our mission briefing for today. We'll be hitting the fragile direct stream, the PubSub tactical roster, topic vaults, delivery guarantees, the idempotency shield, and finally, routing and replay. By the end of this explainer, concepts like asynchronous communication, message ordering, and idempotency are going to feel completely intuitive. So if you've ever wanted to understand how modern distributed systems really work, this is going to be worth every minute. Let's kick things off with Phase 1, the fragile direct stream and the absolute inevitability of network partitions. Let's examine the fatal flaw of basic system communication. If you look at a simple direct stream, like a basic chat application, where clients establish a long-lived connection with a server, it works perfectly fine in a vacuum, right? The server just sends text messages directly to the user. But the moment we step into the harsh realities of massive distributed systems, we have to face a universal truth. Failures are guaranteed. What happens if a client loses connection? What happens if the server suddenly dies? Well, a network partition strikes like lightning. Imagine we aren't just sending chat messages, but critical data like livestock prices that clients are actively relying on to execute highly sensitive trades. In a direct streaming model, if that connection drops, those unretrieved messages, they just vanish into the void. It's catastrophic data loss. We literally cannot afford to lose access to critical operations just because of a temporary network hiccup. Which brings us to Phase 2, the pub/sub tactical roster. Time to look at our arsenal. To survive this fragility, we need a seriously robust defense mechanism. Enter the 4 heroes of our tactical roster. First up, we have the publisher. This is the server or service actually emitting the data. Second, we have the topic, acting as a highly secure vault or channel. Third is the subscriber, the client tuning in and listening for relevant intel. And finally, the message itself, the payload, which could be a simple data block or a complex asynchronous operation command. Now, check out how these stats stack up against the old way of doing things. It's a game changer. Direct streaming has no intermediary and tightly couples the sender and receiver together, leaving it with a pretty weak C rank for fault tolerance. But PubSub? It boasts S rank fault tolerance and S rank message persistence. By bringing the topic in as an intermediary, PubSub takes that heavy burden of persistence completely off those fragile network connections. Let's dive deeper into Phase 3. Decoupling and topic vaults, which provide our secure storage. Let's see how this builds into an unshakable architecture. This right here is the true magic of the system, decoupling. Because we've placed the topic vault right in the middle as an intermediary persistent storage layer, the sender is completely decoupled from the receiver. The publisher doesn't need to know if the subscriber is online, offline, or struggling with a terrible network connection. It just securely drops the asynchronous operation into the vault and moves right along to its next task without ever being blocked. Think of the topic vault as a heavy-duty, bidirectional, persistent database. On one side, publishers push data in. On the other side, subscribers extract it out. If a subscriber's connection suddenly dies, the messages don't vanish into the void anymore. No way. They live safely inside the persistent memory banks of the topic, patiently waiting for the subscriber to come back online and retrieve them. Moving on to Phase 4, delivery guarantees and the hidden threat of duplicates. See, once we start storing these messages persistently, a brand new tactical challenge pops up. Because we are buffering messages, we run into a fundamental law of distributed systems. You are guaranteed at least once delivery. Notice it doesn't say exactly once. Achieving exactly once delivery in the pure chaos of a distributed network is practically impossible. A message will always arrive at least once, for sure. but sometimes it might arrive more than that. Here is the tactical flow of exactly why that happens. Under the hood, the topic vault keeps an index tracking every single subscriber. So it sends message 1 out. Now, it will not clear message 1 from its vault until the subscriber sends back a confirmed acknowledgement or an ACK signal. But what if the subscriber actually receives the message, but its connection drops right before it can send that ACK back to the topic? Well, the topic assumes the message failed. So when the connection is restored, the vault resends the exact same data block. And that brings us to the dark side of this guarantee, the threat of duplicates. If you are designing a system, say tracking likes on a video, and you use a non-idempotent operation that simply says increment counter by 1, a duplicate message is an absolute disaster. If that message gets delivered 5 times because of some network hiccups, it yields 5 likes from a single click. A single mistake here can literally break production systems and completely corrupt your entire system state.
So how do we fix it? Phase 5. Wielding the idempotency shield to protect our state.
How do we defend against this inevitable threat? We equip our subscribers with an idempotency shield. An idempotent operation is basically one that yields the exact same outcome regardless of how many times it's performed. So instead of sending a command that says add 1, you send a command that says set status to complete. If that message hits the shield once, the status is complete. If duplicate network goes hit it 5 more times, it simply absorbs the impact. The status remains complete. Pub subsystems rely entirely on these idempotent operations to safely handle duplicate message deliveries without corrupting your data. Finally, Phase 6, Ultimate Routing and Replay. This is where we get into some real-time magic. Entering the final phase of our mission, let's explore some of the advanced, almost magical capabilities unlocked by this model. Because topics are essentially persistent queues, they enforce first-in, first-out sequential ordering. This is absolutely critical for things like sequence stock trades or reading chat applications in the correct chronological order. But even more incredibly, because the underlying storage is persistent, you essentially have time magic. You can literally rewind the system and replay past messages. If a new subscriber joins, or if you need to recover a past state to debug a critical error, you just replay the sequence right from the vault. On top of that, we have the ultimate technique, routing. You don't just use one vault. You create multiple topics to separate your concerns. You route crucial news alerts to Topic Vault 1 and rapid-fire stock prices to Topic Vault 2. And it gets even better at the subscriber level through content-based filtering. 2 different subscribers can listen to the exact same topic, but apply local filters so their systems only extract the exact subset of data they actually need, like, say, filtering out everything except tech company stocks. So that's the publish-subscribe pattern, a powerful architecture that enables scalable, fault-tolerant, and asynchronous communication across distributed systems. We saw how publishers and subscribers stay completely decoupled, how topics ensure reliable message delivery, and why concepts like ordering and idempotency become absolutely critical in real production systems. This pattern powers everything from notification systems and event-driven microservices to real-time analytics used by millions of users every single day. If you enjoyed this explainer, make sure to like, subscribe, and share it with anyone learning system design or distributed systems. And in the next explainer, we'll dive even deeper into the architectures that power modern internet-scale applications. Until then, ask yourself, is your current architecture truly fault-tolerant, or are you just one network partition away from disaster? Keep learning and keep building.